because like we can't finish this class and never have you guys use an iterative solver. Apologies. Any other questions about it? Yeah. So let's move on to, we're going to shift gears and then we're going to shift down actually and go back to linear solvers again. But let's go ahead with this one. So now we're going to talk about doing curve fitting and interpolation. The goals of today is to explore polynomial interpolation of data, and then I want to convince you guys never to do it, with very few exceptions. We're going to take a look at Legendre polynomials and cubic spline routines. The other one in there is Newton. Newton method has some interesting history to it. It's actually one of the earliest types of computers. The difference engine used the Newton method for these sorts of things. Everything that I've found to date has all been about the Lagrange polynomials. In my research, I use more Legendre. So if I mix up Lagrange with Legendre, that's why. And I see that I already did it over here, actually. Hold on a second. Wrong place. Paste. All right. So the idea behind interpolation and curve fitting. Both of them deal with discrete data, and what you're trying to do, like you're implicitly assuming that there is some actual function underneath these things, right? You don't have the function. All you have are the sampling points. That's your discrete data. How do you recover that function in the best way, right? Interpolation goes about it and says that I want to fit a curve, right? Not necessarily, but for the purpose of this lecture, I want to fit a polynomial that crosses through each one of these points. What that means is that there's no experimental error, right? The measurement is 100% accurate. There is no ambiguity in the mapping between X and Y, which is to say that I don't repeat my measurements and get different answers. If I do repeat the measurement, then I get the exact same answer. How often does that happen in reality, right? In my opinion, its current use to interpolation is capturing local behavior. By which I mean, if you have a whole smattering of data points and you want to know how something is behaving here, then you can interpolate between the things that are kind of close to it, quote unquote, as opposed to curve fitting. Curve fitting is more the best fit to all the data, right? So here we do have some kind of experimental error. It doesn't traverse all the data points, if any of them. To be frank, especially in finite and infinite precision, it might not traverse any of them, but it's still the best fit in some sense. It does allow for ambiguity, so you can actually repeat your measurements, right? Reproducibility. It's more a global encapsulation of the data because now you're actually looking at the curve as a whole, as opposed to the local behavior. I debated even including interpolation as a separate topic in the lecture series because, to be frank, most modern curve fitting, like you have a tuning parameter that adjusts what kind of fit you're going to do for the data. We're going to get into best fit and least squareds next lecture, right? But if you tune it all the way down, then you are exactly reproducing the interpolation polynomial. As long as you don't have any duplication, you don't worry about the experimental uncertainty. So in modern implementations, the curve fit kind of includes interpolation as a limiting case, as an ideal case. But this is the way it's been taught. This is a way that some of you might eventually run across. I am honestly not sure, right? But I have to give you the tools anyway. So interpolation is historically easier to do. That's kind of interesting because that means like kind of the interpolation came first. The reason behind that is that curve fitting kind of you need all the data as a whole. And if you have even if you have like 10 data points, right? Unless you're plotting them and then using a French curve to draw a line through them, like you need some kind of like significant mathematical apparatus to be able to chew through these things. In terms of comparison, we're going to be looking at the speed of building the model in the first place. Yes, they're going to be polynomials, but there are actually different ways of building those polynomials, adding new data to the polynomials, and then executing it and actually solving for your value. For the cases that we're going to be like looking at in the demonstrations, it's basically trivial because we're not going to be looking at very large systems. So again, you kind of have to imagine that you're doing these for, 1,000 data points, 1,000,000 data points. Then it really starts to become interesting for that. Okay, one of the fundamental, I couldn't find I couldn't find somebody that was named for this. I just found it as a fundamental property of linear algebra, is that it's always possible to construct a unique polynomial of degree n that passes through n plus 1 distinct points. So order n minus 1 through n or n plus 1. Key point there is that it's a unique one. So we're going to talk about 3 different polynomial fitting algorithms. They are going to produce different expressions for the polynomial, but if you simplify it down, you're going to arrive at the exact same one. Necessarily, you don't have a choice. Okay, our toy problem that I'm going to introduce up here and then skip down until I actually compare everything is going to be a Gaussian. Here's my Gaussian. Here I am sampling, I think there's 11 points there at interval of 1, and I'm just collecting that data. And here I go. And the idea is, how would I best be able to recover this blue curve only given the red dots? Okay, Lagrange polynomial interpolation. The idea is that we're going to build our interpolator function as a linear combination of these basis functions. Again, we're back to basis functions. Each basis function gets a little bit messy, but here it is. So first of all, the entire polynomial is the sum of all these basis functions weighted by, it turns out, the actual data point, which is kind of a neat property. And then, but the basis function itself is this product of. Have you guys seen this before? This pi? Okay, so like sum, now a product, and it gets kind of lengthy. These basis polynomials have the property that p is 1, where, oops, that should be a j in here. So when I is equal to j, when the ith basis is evaluated at the ith data point, it's going to result in 1. When it is not equal, then they're going to be 0. That's why when you sum everything up, it just works out to kind of have this nice property that the overall function is just a sum being weighted by those data points. So at least that part is easy. When we churn through this equation, and it is a bit of a churn, what you get are, for example, for data points here, you get the 3 basis functions, and they look kind of messy. You get a bit of cancellation, a bit of some of the terms are 0. So here are your expressions on the other side. And when you plot them, you see that yes, in fact, P1 is 1 at that data point, P2 is 1, and then it's 0, likewise for the other one. So we're just confirming the property. Yeah, I don't need that anymore, actually, so I'm going to skip past that. And then when you, oh no, what happened there? Oh yeah, old friend. Evaluate. 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 Oh, come on. It's a problem with live demos. Yes. Yep. There we go. So when you add up all these polynomials together and you do that series, lo and behold, you do get a function that actually passes through those points. There are 3 data points. So what kind of polynomial is this? Yeah. What? Parabola. It's quadratic, right? If there were 5 data points, what kind of polynomial would this be? 4th order, right? Like and it has to be that. So kind of the interesting thing about the Lagrange polynomial basis is that when you do that, it actually does result in this, which is kind of neat, to be honest. Very smart people. All right. So yes, sure enough, for n data points, we do in fact produce the unique polynomial. Great. If we have two measurements at the same x value, what ends up happening is that you get a division by 0 here, right? Xi minus xj, if xi is equal to xj, you get divided by 0, the thing falls apart. Unless yi is also equal to yj, in which case you're doing a limit thing, but practically you just drop that term entirely and you don't have to worry about that anymore. Come on, it's going down. Okay. Every evaluation, whenever you calculate p, you end up doing how many multiplications? I feel like I should be playing the Jeopardy thing. Whenever you're calculating p, remember the product is the product of all these terms, and you're going from 1 to n, avoiding where j is equal to I. So you end up doing n minus 1, which is order n calculations. And how many of these bases do you need? Here, right? So your overall complexity is n squared. That's for the assembly of these things. That's for building these things. Adding new data means you have to restart the calculation all over again. And that's a bit of a pain. Again, this is one of those things that, like, think about it in terms of before computers came along, when somebody actually was like calculating these things by hand. Now, all of a sudden, like going through all those steps again and trying not to make any mistakes actually becomes kind of formidable, right? So this is why they came out with Newton. The other thing I wanted to show you is this is using SymPy, which is the Python symbolic library. One of the values to having these different techniques is that if you do want to use symbolic logic for whatever reason in the future, then at least you'll know like where it comes from. When you do this, SymPy simplifies very, very poorly. Takes forever, so it never simplifies. When you build these things, this becomes your equation for that fifth order term, and it's massive and it's huge because we haven't simplified. If you do simplify it, then you get down to this nice quartic equation, right? So one of the magics that we're going to be doing is, can we just arrive at this expression directly instead of having to go through all the simplification step? Another important feature, important for mathematical analysis, I'm not going to be quizzing you guys on this one, is that we can see, if we look at the error for this, we can actually say, we can set an error bound on how good this approximation is to the data. Flip point is that for any set of data, we can fit a polynomial, which can be expressed in Lagrange polynomials. And therefore, this has like general application. So if you look at this, it's a pretty funny expression, not going to lie. There is a variable here that basically this xi variable takes any value between in the entire range. Not so important. The important part here is that the further the data point is from the point that you're evaluating, the larger its impact is going to be on the error. And that's kind of a bad thing, right? So if you have data points that are here, 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 and you want to know the value over here, the majority of your error is going to be coming from this data point, which is a little bit funny and a bit counterintuitive, but there it is anyway. And this is a property of all polynomials, all polynomial fitting. Okay. We can improve the computational complexity of this. So Lagrange polynomials, that's kind of like the basis, but they're computationally difficult because of that n squared. you can do some simplifications, and that's what I'm going to talk about. This is the one that's actually used in SciPy. They use something called the barycentric Legendre polynomial. Basically, what you do is you do some factorization. So you pull out this product, and you end up simplifying it down. You define a few other terms, and this is what you end up with, this type of expression. So this is, again, this is the interpolated value. Here's your omega function, which is the product of all of your data points minus whatever your evaluation is. And then now you have a sum. And you have a sum of your wi's, which are your weights. And you have your difference here. The nice part about this is that wi can be pre-calculated. And it's a product. So in doing this substitution, you've lifted out this giant product evaluation and you've pre-computed it once at the beginning of your calculation, and then you're applying it over and over and over again, which is a big saving, and which actually means that you only have order n for evaluation. So we've saved an order of n, which is, or we've gone from order n squared to order n, which is huge to do that sort of simplification. And that's because the W has been lifted out of it. Let's see. So building it still takes order n squared because you have to assemble these things, but then your execution is a whole lot faster. Yeah. Another interesting property about this, by the way, this isn't in the textbook. The barycentric formulation isn't in the textbook, despite it being like kind of the norm. Right now, I had to pull out another paper that all the other things were actually built on. So I'm going to put that paper into the lecture notes so that if you guys are interested in how all these things are derived and the commentary on it, you can take a look. You don't need to be frank, because that's kind of next level. Like, we don't need to know that sort of thing. But that's actually where all this mathematics is coming from. Okay. We can keep going. We can introduce another variable or another equation, another piece of data, that being the equation for 1, which should be the trivial function. So, and if we say that 1 is this kind of degenerate case, still expressed in terms of the Lagrange polynomials, we can divide everything through. So that should be y, not f. This is actually the form that's implemented in the computational libraries. The nice thing about this one is that we've actually canceled out omega. And omega was this product of differences. Guess what happens when x is equal to xj plus a little bit? Think back to like the first or second lecture. If xj was 0 and x I wanted to evaluate at 1e minus 16, what do you think would happen when I put that into the computer? It's just going to drop the precision, right? So when that happens, and this is products. So if you get too close to one of your data points, you get something called subtractive cancellation. And all of a sudden, you're subtracting different orders of magnitude, and the entire thing collapses. Now you have a 0 sitting in front of a product, everything dies. When we cancel out omega, we remove that. So this implementation is actually a lot more robust because we don't have to worry about x getting too close to the data points, which is really nice. Okay. Any questions about Legendre polynomials? No? Okay. Newton's polynomials. Before the barycentric formulation came out to kind of alleviate this whole order n squared, Newton came along and started to derive his formula. And that actually, the interesting thing is that it's also called the method of divided differences. And we're going to see why. And that was actually the algorithm that before, I don't even know if that would be the time of the slide rule at that point, before computers were out at all, people would, like, if you wanted the logarithm of a number, you would have to pull out a book and look in the back chapters where they would have tabulated that. Those tabulations were calculated using divided differences. And when Babbage? I think the Babbage difference engine came out. That difference is divided differences. That's where the machine gets its name from. So this is like progenitor of computation, computational material, math, numerics. Okay. Given that any polynomial can be written out like this, right? You've got your coefficients, you've got your terms. If we write it out in this form, we have the advantage that we can do nested multiplication. So does this simplification make sense to everybody? In the case of 4 terms, all we're doing is we're grouping things and we're putting it inside and then we're multiplying out by another factor in front of it. And what that means is that we're not duplicating all these multiplications, and therefore evaluation of these things is order n instead of order n squared, which is really nice. Okay. The way that they calculated this is they picked a data point to start at, say it's x naught, and they say, okay, with just x naught, all we have is, sorry, this should be y, and this should be y. All we have is y at x naught is equal to a naught, which is equal to y naught, right? Trivial solution. When we go to insert another data point, what we end up getting is y at x1, a naught plus a1, x1 minus x naught. That equals y1, and we can rearrange this for the coefficient a1. And what we end up getting is this in terms of a naught. When we add on another data point, we've again iterated on this, and we can solve this recursively. So what you end up getting is this recursive structure generating your coefficients of this matrix. And in particular, it is the difference divided difference. All the way up to A3, you can see that there's a pattern emerging, right? In general, if you write it out in this format, so you've got an interpolation function is equal to that, right? The ternary equivalent is you can decompose in terms of the binaries, right? So there's your difference in binary, and you can always do that. You can always decompose your n in terms of your n minus 1s. Divided difference of n minus 1. And we can visualize that. So this is commonly where you'll be able to see like the divided difference technique coming in. So x naught, y naught, there's a values, right? This is kind of the first level where we're just doing the difference between these guys. Second one is the difference between the ones to the left, and you go on and on and on all the way to your overall function. You can put it into a matrix. And they're like, I've seen this matrix being written 3 different ways. There is some matrix algebra that you can do with this, but generally you just look at it as a way to tabulate things. What ends up happening is that your coefficients are actually the diagonal of this matrix. The nice thing about this matrix is if you add more data onto it, what you end up doing is adding on another diagonal, right? Because everything is made up of the things to its left. If we add another data, right, we toss it on top, and then we cascade it, and we do, well, the difference between that one and that one is there. That one and that one is there. That one and that one is there. That one and that one is our new one. Add on another data point. Now we've slapped on another diagonal. That one there, that one there, right? And you're building this up from a single data point into larger and larger and larger. That's a real advantage of that. If we chose a different data point, so there is no set order that we're looking at these data points. You can just choose whichever one you want. Obviously, there is no like transcendental meaning to any of this. What you get is a different tableau. You get different coefficients, but your diagonal is still going to be the same because it's a unique polynomial. Yeah, adding new data means recursive doesn't require recalculation of the others. So in Legendre, before we did the barycentric one, if you added on a new piece of data, you would have to recalculate everything. Barycentric means you don't have to worry about that. Newton was always designed with that feature, which is, again, nice when you're doing all this stuff by hand. Let's see, assembly still takes O(n)² New data points take ON and evaluation takes ON. And the coefficients are independent of X. Well, obviously. Okay. Any questions about Newton? Okay. There's also direct solutions. And the direct solution logic looks like this. So now we're into the era, we're past the difference engines, and we're into more kind of modern computing. We know that there is an equation that looks like this. You've got your coefficients, you've got your powers, right? If you have 5 data points, you have 4 terms. Well, you have 5 terms, 4 powers of X. We know for every one of the data points, this is satisfied. Y at xi, blah, 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 is equal to yn. Do that for all your data points and build a matrix, right? I told you we were coming back to linear algebra. What you end up getting is a system like this. There should be another one on there, whatever, right? This is a linear system which can be solved. And we know how to solve linear systems because we've just been doing that for the last 2 weeks. This particular formulation, this type of matrix is called the Vandermonde matrix. It is notoriously ill-conditioned. So yes, you can do it, but what kind of direct solver are we going to be throwing at something like this? What's good for ill-conditioned systems? Dense solver, yes, definitely dense. What kind of dense solver? LU. That's right. That's always going to be the answer. LU solver. You throw it at this, and it's still going to have problems because it's still ill-conditioned. Shoot. Yeah. Effectively. Yeah. Thank God. Exactly. The biggest benefit to iterative solvers that I found is using HPCs. Because that's how we can get the distributed computing into something.
Out of curiosity, sorry, I'm just
Hold on 1 second. Hold up 1 second. Is that about this one, or is this about iterative solvers again?
I was asking no,
let me come back to it later. Okay. Does this matrix make sense to everybody? Right, we're just assembling it line by line, putting it into a matrix and inverting it. Yeah, it's ill-conditioned for large N. We're going to be coming back to this one on Wednesday. This is actually the way that modern computers do it. But we're going to come back to this one once we talk about pseudo-inverse. Okay. So we have 3 methods that all generate necessarily the exact same polynomial. Let's see what that polynomial looks like. Let's return to our toy problem and run it. This is the Gaussian. The blue is nice here. You can see kind of the tail poking out here. Here's our data. And the unique polynomial that interpolates all that data behaves terribly at the end. You can see there's this nice oscillation, and any kind of extrapolation outside that range is awful. That is a phenomenon called Runge's phenomenon. It appears so many places that it's been given a name. And it is the case of even like the most basic type of sampling. Like equiaxed or equal spaced samples is not very common. And even then you get these massive oscillations. And those oscillations come from the higher order polynomials. Right? When you start to get more and more of these data points, your polynomial ends up going like this. What can we do about it? Enter splines. The idea with a spline is to get rid of the oscillations. So because Runge's phenomenon only kind of becomes apparent for higher orders of n, we're going to reduce the order of n, and we're going to instead do piecewise functions. What we're going to do is we're going to require smoothness, right? So the idea behind splines is, I wish I had a ruler or something, but can I borrow this for a second? Right? A spline does something like this, literally, right? So what can you say about the spline? It's smooth. Smooth means what? 3 types of smoothness that we're going to talk about here. What's the first kind of smoothness? Between if you imagine this is one function and this is another function, how would you say that it is smooth? They're continuous, that's one. What's the next? Which derivative? First derivative is continuous because the slope has to be. Anything else? Second derivative is also continuous. And the idea is that if you have those four pieces of information, right? So you have the values that are fixed to your data points. That's 1 and 2. And then you say that between those elements, you have continuity, which means, first of all, that they're equal, but that's we've already said that. And then it's smooth, first derivative and second derivative, both continuous. Then you have four pieces of information. Four pieces of information gives you what kind of polynomial? Cubic. Cubic spline, hence the name, cubic spline. Okay. What we end up doing is describing the spline. So what we're going to do is a piecewise cubic spline interpolation of these things. In order to specify the splines, we're going to use pieces of data that are called knots, right? It becomes a knotty problem. That turns out to be, for this particular case, I saw one laugh. You can tell I'm a father of two. I like me the dad jokes. The knots in this particular case turn out to be the value of the second derivative at your data points. That is not always the case. Different splines, you've probably seen these at some point. Like you can do a lot of CAD software, any kind of vector graphics, you get like kind of the I don't know if you guys have ever seen something like this. So that's your point. You get these kind of like levers out there. Have you guys ever seen that in like graphic software, vector graphics, or CAD or something like that, right? These are not the knots, nor is this guy actually. The knots are kind of like another abstraction that specifies that cubic spline. Splines in general can also not have to go through the data point. They can be a curve fitting algorithm too, but we're not going to talk about that one. This is just standard cubic splines. The approach behind the mathematics here is if we say that the second derivative is continuous, then what it means is that the second derivative is going to be piecewise lines behind all these elements. So there's one element, there's another element. Because we're talking about second derivative, it is continuous here. Express the second derivative as a Lagrange polynomial, right? Throw back there. Solve, integrate, make everything continuous. I'm not going to go through the math. Nobody wants to see it. It's in the textbook. And what you get is an expression like this. So this is an expression, again, we're going through the different elements of K, right? And we've got these coefficients in that specify things. And then the data on the other side, we've got a linear system. What kind of matrix is this? What kind of diagonal? Tridiagonal matrix, right? We can solve tridiagonal matrix, and importantly, it is sparse. Very useful. And we would solve it with a bonus points. Sparse LU. Correct answer. All right. When we do that, let's just use the NumPy, or sorry, the SciPy implementation. And sure enough, we get a better answer, arguably, in that we don't have those high frequency oscillations. But we still have some funny business going on at the ends here. In general, interpolation is just that, interpolation, not extrapolation. Doing any kind of extrapolation is notoriously sketchy, to be frank. The reason why it does a better job is that they're considered stiffer than n-degree polynomials in that they don't have those higher order terms. Therefore, they avoid the Runge phenomenon. The concept of smoothness is easy in 1D, right? it is continuous, C0 continuous, C1 continuous, the slope is, and C2, right? You can imagine trying to generalize that to 2D, right? Now we have, imagine you're doing a patch. So you've got 3 data points here, here, and here. I have a whiteboard. Okay, so now let's try and do 2D. Say we have pretty simple data, right? We're going to again do a piecewise cubic something, which means that we're going to have one piece here and another piece here. What does it mean for these two functions to be continuous along this edge? Right? How would we parameterize that? How many data points, how many knots would we need to specify that this would have to be the same here? Then you add on the first derivative. Then you add on the second derivative too, and this becomes a giant mess. Right? It's pretty difficult. We're actually going to be talking about that in the finite element part too, because this is basically finite element at this point. Therefore, cubic splines, there are, I think they're called bivariant splines, and that's valid for 2D, and that's it. Don't go past 2D. I think bivariant splines are not interpolation; they're more curve fit, right? So that you can reduce the degree of information that you need to put into those patches by saying that, look, it doesn't actually have to cross that point. We can instead do it as a best guess while maintaining that smoothness. Okay. Because so smoothness kind of implies a holistic approach to this. We cannot just consider these data points. We also have to consider the neighbors on either side, and those neighbors consider those neighbors and their friends and their friends and friends and friends, and you end up with a global situation. That's why you need the linear solver, because you're doing a simultaneous solution to all that, which is hard, right? And that's why splines have only really come out since what, punch cards, basically. Okay. Generalization to n dimensions. Here's the disappointing part. First of all, for any endpoints, there is still a polynomial that fits it, but because of Runge's phenomenon, you generally don't want that. Right? Instead, what you would want is something that's a lot stiffer so that you don't get these high frequency oscillations. The problem with that one is how you generalize that to n dimensions. Everybody knows what I mean by n dimensions, right? Yeah, okay. So what do? The standard packages actually have very few options. The simplest one is nearest neighbor, which is super simple and literally says, if you want to know it here, well, it's close enough to that one, so you get this. And if you do this nearest neighbor algorithm, I wanted to get around to it, I just didn't have time. What you end up is getting this kind of nice patchwork mosaic of the different reasons that all these things kind of define, which is kind of neat. Not really so useful, to be entirely honest, but very quick to evaluate. The other option that you can do is a linear ND interpolator. And this is what like NumPy and SciPy implement. Effectively, what you end up doing is, I'm literally holding a little marker, a little eraser here, but I'm still doing it. For a given point here, you triangulate which patch this falls into, and then you do a linear weight of all of your data points around that patch. It is a barycentric linear version of Lagrange polynomials, right? That's what it actually does. Of course, because it's linear, now you get this faceted behavior between different data points because there's no continuity, there's no smoothness, but it's very robust. I don't know about you guys, but none of these are particularly satisfactory. Right? Like you would want something else. To get somewhere else is more complicated, and that's what we're going to start talking about on Wednesday. One nice tool is something called radial basis functions. That's a bit more advanced. Now we're out of the realm of polynomials, but we can still do lots of cool stuff. But to get there, we need to talk about curve fit first. Any questions? Which commercial softwares? So CFD is notoriously difficult to solve, right? So here's where we can talk about the iterative ones. There are preconditioners that are specifically designed for CFD, and they take information like the, help me out, what are the what's that? No, not Navier-Stokes, they're the numbers, they're the constants. What's that? Yes, yeah, Reynolds number, I think Paclane number is a number one, is another of them. Like this is why I say that like preconditioner is actually a very active area of research for this sort of thing, and it's specifically for that. So that you stand a chance at that sort of thing if you're using a very well-studied type of physics, and if you have preconditioners specifically built for that. So the preconditioners that they use are not ILU. They use something else. They probably also do like finite element model, in which case you get other properties. So the way that you're even discretizing the differential equation in the first place becomes different. And then that also adds to the stability of these things, right? But that becomes like very specific, and then you're just doing a course completely on Navier-Stokes. Yeah. But if on the other hand you try and do that, and then you add in temperature, right? Unless you have a preconditioner that is specifically built for that, then you're doing this whole block inversion operator split methodology, which is super sketchy, to be honest. So then again, you can have like different simplifications. You can do like a linearized temperature. Maybe that'll work. Maybe it won't. But yeah. Yeah. Stefan, you had other questions about iterative HPC?
No, it was more related to locally solved ones that can take advantage of like shared memory.
Yeah.
Like how useful those, like have they not started taking the advantage of those? Now, for example, like 390 has some 80 teraflops, whereas the C32 cores will have only 1 teraflop. So isn't there something
way out of my field, to be honest? I know that PETSI, the linear solver library that I do use, does have TPU and GPU and TPU in there now. I shouldn't say it because I'm not 100%. As I understand it, the problem is not the sheer number of calculations that you can do. It's passing that information around between those calculation units. And that's kind of like, that's the issue with linear solvers, as opposed to stuff like graphics, right? Because one photon, one ray traveling through space is kind of independent of all the other rays, right? If you're doing molecular dynamics, which is basically you're taking billiard balls and you're playing pool with each other, this one doesn't care about this one over here. So it parallelizes with GPU much better than linear solvers do. But it's because that linear solver has the holistic information that becomes the problem. Unless you do domain decomposition and then you're into linear, and then you're into iterative solvers. Yeah. Anything else? Good. See you guys Wednesday. Last class, I think we ended off with the pseudo inverse, right? Okay. So just to recap, the idea with that one is even for a rectangular system, even when A is rectangular, you can still solve this system. The problem there is that you can't solve it exactly. What you're doing is you're minimizing the way that you're not solving it, to be honest. So whereas AX minus B is your residual, we are going to minimize the residual, and the ultimate minimum is 0, in which case you have recovered the exact inverse. But this is a much more general object, the pseudo inverse. It is calculated using something called singular value decomposition. It's not actually calculated like this in practice, but that's another level above. It's basically the generalization of eigenvalues to rectangular matrices, and both of those are kind of advanced topics, so let's not go there. Okay, doesn't mean that we can't use it. One of the things we want to use it for, we cannot escape the condition number of the matrix just because it's rectangular. So because the matrix is rectangular, the determinant is not defined, right? Determinant only for rectangular matrices. Yeah, I'm recording. I'm sharing this one. We can still talk about the condition number. We can't escape the problems with the numerical accuracy and finite precision. So in that case, the condition number is generalized to include the pseudo-inverse. Pseudo-inverse is typically, I hope you guys can see, this is a dagger up top. That's the standard symbol for the pseudo-inverse. So it's the norm of the matrix times the norm of the pseudo-inverse. And that's still exactly the same criteria. It has to be roughly 1 in order to be numerically stable. Okay, some terminology. A consistent system of equations has a solution that satisfies all of the equations. So in this case, I'll show you guys an example of a consistent set. But basically, that solution, even though it's a rectangular matrix, you can still find an exact solution, which is kind of neat. But I'll show you what, actually, we've already seen. This is our head scratcher from the early ones. An inconsistent solution is inconsistent. There is no single solution that satisfies all of the equations. So what we're reduced to is doing kind of a best fit. The problem is that that doesn't always mean that that best fit will actually mean very much. So one condition that you'll encounter is an overdetermined set. This is very common for curve fitting. This is my alert to pay attention to what I'm saying. Right? Generally speaking, you have more data points than you have parameters that you're looking to fit. Right? For example, any function that you're looking for, you're going to have 100 data points and you're going to fit a quadratic. That's an overdetermined system of equations. So you're going to find a best fit. The counterpoint to that is an underdetermined set, in which case you have 2 data points and 3 pieces of parameters. So now you're fitting a cubic to 2 data points. So you can either always find a solution, you have an infinite number, or you have no number. And in that case, that's the case of the parallel lines. For example, where there is either they're overlapping, in which case you have infinite, or they're parallel, in which case they never meet. Yeah. I actually had a paper maybe 6 or 7 years ago where somebody tried to fit 2 pieces of information to 1 data point. And like I rejected it on the grounds like, come on, guys, this is first year undergrad. Like, come on. All right. So going back to our original head scratcher, I think this is from the lecture number 3, right? This is chairs and tables. I'm not going to go through the whole thing again, right? We have 20 chairs, or I think, what was it? The chairs cost $20. The tables cost $50. That has to make 700. Total number of items is 20. Some excuse to have this other equation. That gives us the linear system here, right? Because this is, okay, so our vector of unknowns is C and T. There it is there. We have 20, 1, 1, 50, 20, and there's our values on the other side. And what we wanted to do is, first of all, plot it. All this stuff is very useful to plot because you can see, like, plotting is so easy, especially now. I think I even used, maybe I didn't use Gemini for this. But it was simple enough that even I can do this, right? Like you can just like ask Gemini or ask Copilot or whatever to plot it. And you'll see very quickly what kind of system is this. It is overdetermined, but more importantly, they are linear systems. Is this a single answer? Is there going to be one answer that satisfied all of these equations? Yes. Right? And it's the point in the middle. This is a consistent one. Okay? So let's go through a lot. There's the answer. So here again, I'm trying to do the whole like, let's have a chance to actually program this in, but then let's actually have the answer down there too. Right? So we say that N is, or A is the NumPy array. NumPy doesn't really care about the, like, it doesn't require a rectangular matrix, or it doesn't require a square matrix. NumPy is just about like arrays of n by m by whatever you want. You can actually go multi-dimensional too. And Copilot is even smart enough, or Gemini is even smart enough that it's auto-populated that. Okay, so since it populated it for me, it's going to do it for you too. Great. We solve it, and we get an error. Oops. We get an error because I didn't close the thing. Okay, so here's our matrix A. Here's our matrix B. What do we do when we have a matrix, sorry, vector B? What do we do when we have A? We're looking for X, we have B, we put it into linalg.solve. Linalg.solve A and B, and it gives us an error. Why is it an error? It says it right here. Front row. It's not a square matrix. It literally says that it must be square, right? So this particular algorithm is not the correct algorithm for this. What we want to do is form the pseudo inverse. And what we would have to do there, again, don't look at the answer down there. We go back to our system and we say, okay, we want the inverse of transpose times the matrix. Invert that and multiply that by the transpose. So let's say, let's comment this out because it's wrong. Let's ignore my answer down there. M is equal to, we can still do numpy linalg. Look at that. It's literally giving me the answer as I go. Okay. Numpy, linalg. This is what happens. Like I try and do something where I try and do a live demo, and either like the live demo fails or AI is just auto completing it for me. But okay, whatever. So we're still going to, so we're going to form this matrix A transpose multiplied by A. Remember this, the puppy symbol? Is that right? The A transpose puppy A is matrix multiplication, right? We're going to invert that. So transpose times the matrix gives you a square matrix, generally invertible for other reasons, right? We're going to multiply that by A transpose, and then we're going to, I mean, we can look at that. Did I do all that? Oh yeah, I guess I did. Okay. Right? That is our pseudo inverse. And we multiply it by B, and sure enough, we get our solution 10, 10. We look back at our plot, 10, 10. Yes, that is the consistent solution. Great. Rather than doing this, feel free to use the linalg.p invert, right? P for pseudo. You can check. So this is my preferred way to check if two quantities are equal whenever they're numerical, rather than trying to say like, is M equal to NP linalg.p inverse A? Rather than doing that, subtract the two and visually take a look at that matrix. So this is the matrix here, and this is small. Anything less than 1e minus 16, you're out of, what is it, floating point precision. At least I think single is 1e minus 16. But either way, like this is small, therefore they are the same quantity. You're never actually going to get the same one. Okay, so numpy, linalg, p invert, give you the same answer. Shoot. I'm gonna hazard a guess yes. Yeah, I wouldn't. What equation did you have, or what?
So
what did you
at
have?
the top, like
Yeah.
A and B, I added a 0 after the 50, and after the 20. So like, and then I added a 1 to that.
Where? Sorry.
Added a 0 after there, so like
Yeah.
20, 50, 0.
Okay.
Added a 1 to the
0.
Added 1, 1, 1.
Okay.
And then I added a 0 to the third one.
Okay.
That gave me 10, 10, and then like some like absolute like either the negative 20 like number. I don't know, I'm just curious. I was trying to.
So what you've done in that case is actually added on another term to
Like a term
those
like
equations.
shares.
Yeah,
Like a
you've
term
added
like
shares,
shares.
tables, and light bulbs. And what you've said then is light bulb is equal to.
Like what, like by putting zeros there, the light bulb should just be 0.
Yeah. So I don't know if that's going to work in general.
Okay, I'm just
I wouldn't. It might be a case of only working for consistent equations, and unless you know that going in, I wouldn't bother doing that one. But that's a good question. Honestly, don't have a good answer for that one. Okay. Let's look at an overdetermined inconsistent linear system. Okay. So we're doing the same thing here. I changed the $50 per chair or whatever this is to 60, right? We go through, let's plot it again, and here we go. Where do you think the solution is going to be? Intuitively. Solution doesn't exist. Okay, that's one. Anybody else? Any points in that area? Okay, that's another one. That's least wrong. By what metric? Define least wrong. Equidistant to all three of them. Like, this is the solution to line, what is this? Blue and green. This is the solution to green and orange. And this is the solution to blue and orange, right? So you would expect, like, equally wrong in that context is going to be somewhere in there, right? Okay. That's, I thought the exact same thing. I was wrong. And I had to stare at this guy for a while. And then I clued into what was going on. The least squares, so you had the right idea that it was least wrong, but in this case, the least wrong is defined by the residual of that equation. So it's kind of tempting to think exactly as we logic, right? Solution 1, solution 2, solution 3, the middling solution must be in the middle. But that's not what least squares do. Least squares is minimizing the residual of those three equations. So general rule, with most approximate methods, the moment that you start to move away from an exact solution where all those residuals are zero, like we have three equations, right? Three equations, three residuals. The exact solution is where R1, R2, R3 are all equal to zero. The moment we move away from that exact solution, we get other funny business kicking in. And that's what we're seeing here, something called weighting. So we are minimizing the residuals between these equations, but there's a subtle problem. That being that the coefficients of this middle term are actually very, very different from the other ones, right? You actually have like an order of magnitude difference. We could, in the exact solution, we could just take any equation out there, multiply it by infinity billion, and have the exact same answer, right? When we have a system of equations with an exact solution, we could just take this middle one and multiply it by negative 200,000 million billion and have the exact same answer. But because we're doing a numerical technique, we can't do that. What we could do, we could multiply it by tens, right? And that gives roughly the same answer. We could divide the other two, right? What does this remind you of? We're taking a system of equations and we're just kind of multiplying through by scalars for each one of these. We've covered this before. Question at the back. What does this remind you of? You walked in late, so I got to pick up. Okay, which kind? I don't know. What about preconditioning? There was one preconditioning technique. By the way, people online, I'm about to go to question you guys next. So you guys better perk up here.
Is it diagonal dominance?
It is almost diagonal dominance.
Is that the one you're talking about, though? The one that we talked about before that's similar?
Well, what's similar to diagonal dominance? It's the simplest, it's the most basic type of preconditioner.
A Cuvbe? The
Cuvbe preconditioner. This is diagonal scaling. Thank you, Ethan. You're off the hook. Everybody else who's on the call, you're next. I'm telling you now. I got your names. What we're doing is effectively we're preconditioning this system. And again, like preconditioning, blah, right? We just saw this. It's kind of terrible. This is called weighting. This is a weighted residual at this point. And the weighting gives preference to certain equations. In the context of fitting a polynomial or fitting any other function, it gives preference to certain data points because every equation defines one data point. So what we're going to be doing is we're going to be multiplying through by this preconditioning matrix, which is just a diagonal matrix with the weights in it. And let's take a look what happens. Oops. So again, we've got your matrix here, the vector there. Without the preconditioner, we see the exact same thing. Let's do a preconditioner. Again, we're working with the inverse thing. And here's the answer again. Good old Copilot or Gemini, right? We're going to create a diagonal matrix with a certain weight to them. 70 is, in my opinion, a good number to go with because if you take this condition, if you take this coefficient and this one, right, 20 plus 50 is 70, 60 plus 20 is 80, probably the weight that you're looking for in between those two is going to be something on the order of 75, right? Everybody likes round numbers, so let's go with 70. So we're going to take a matrix. We're going to design one that looks like this. I always, whenever you guys are solving for this, like just print out the matrix because usually that'll tell you a fair bit about this, right? There's our weighting matrix. We're going to apply it, which means A is equal to PI puppy A. I'm totally using the puppy thing for now, right? We also need to do it to B, right? Preconditioning goes on both the A and the B vector, which is equivalent to saying, let me write that one down. Okay. So what we're going to be doing is we're actually preconditioning the residual, right? Which means preconditioning AX minus B. But since we have these terms separate, we want P times AX minus P times B. So we've got to apply that to both P and B. Sure. And then now we get it in the middle. So what this means is if we wanted, oh yeah, and here's the next tip too. Python NumPy does have, like obviously, it has functions to do these least squares. So the analogy to using solve for a dense matrix, if you're considering like using the inverse, the pseudo inverse, and then multiplying the pseudo inverse, the equivalent function here is least square. LSTSQ, right? The exact same syntax, otherwise A and B, and you're going to get your solution. It pops out. Just be aware that it does pop out some other outputs too. You don't need to worry about them. Feel free to dig through the documentation and see what else it's giving you. It's giving you other information about the system. You don't really need to know. The first one is what you want. Okay, let's play with this a little bit. Let's turn up the weight. If we make this very large, we are going to move. Now this is a little bit funny, right? Like by making the weighting large, we're moving the dot closer to this orange line, right? And you might not be considering that, right? We're weighting it heavier, but it's moving away from this point. The idea is that what it's doing is it's moving it towards these two solutions equally. And the way it moves it towards these two solutions equally, remember it's the orange one that we're playing, right? By moving these two equally, it means that it's moving kind of towards this orange line. Similarly, if we make it smaller, I mean, we just saw what happens when we make it smaller, but let's do it explicitly. It's going to turn down the significance of these equations and allow it to move closer to it. And this is what we were to start. Okay. What the? That wasn't what I was expecting. Where's everybody? All right, people online, I need a volunteer. Somebody come off mute or I'm picking on somebody. Stefan, there you go. All right. So why would you ever want to use weights? I hope you guys can see this. I hope you can see me doing my hand signals. Why would you want to do weights?
I would say because sometimes, I mean, in my understanding, you care more about some variables than others, so those changes may affect your answer more.
Not variables. This
Elements.
isn't about variables. This is about equations, and each equation corresponds to a data point. So what you're doing is preferring certain what? Nathan, you want to jump in?
Maybe so you could like take away like if you have outliers or
Yeah,
and you prefer the like some extremes, you want the kind of more average.
right. How would you quantify that? Nathan, go ahead, or Stefan? Okay, how about Jason? What do you think? You thought just because you're online you don't get called on.
What was the question again? No, okay. In all seriousness, I did hear it. It's just I lost track.
Oh, good. Oh, good. So why would you, so the weighting determines the importance of certain equations, which means certain
Okay.
data points.
Mhm.
How would you quantify the importance of certain data points? There's a term.
I
for it.
guess mhm.
If you're doing an experiment and you're recording data points, right? You're never going to get an exact number. You're
Right.
going to get a number plus
Oh, the
uncertainty
oh, okay.
or the variance, right? Or
I was
the
gonna say
error.
I was gonna say round off.
Well, round off. So this is in reality, not our computational reality, but this is actual reality. Whenever you do one of these experiments, you're always going to get some kind of uncertainty, right? And under certain circumstances, your data points are going to be much more uncertain, because you have a temperature probe and it's going 300, 400, 300, 200, 300, 350, right? So like, okay, that's like 300 plus or minus 100. Right? Versus another measurement that's like 400, 401, 402, 399, right? Like that's like 400. And you will trust that data a whole lot more. More advanced than this course would get to. That would be a stats course. I could imagine that one, but I would say for now, let's stick to the case where you've done an experiment and you've gotten an uncertainty and you've recorded that uncertainty, and now you want to weight certain data points more heavily than others based on that uncertainty. You guys online can see me doing my my little hand thing, right?
Nah,
Excellent.
can you do it some more? We can't see.
I think I should be jumping up into the camera or something now.
Yeah, I would like that actually. Stand on the desk too.
Yeah, what's that? Oh, rings with bells on. I like it. Okay. So yeah, that's the whole idea behind weights. Let's go a little bit more interesting. Let's return to our polyfit example, right? So as you recall, when we have a bunch of data, we can always fit, if we have 10 data points, we can always fit a ninth order polynomial, which has 10 terms. Always, always, always. The problem with that is that we get this frenetic behavior associated with high order oscillations. So we never actually want to do that. Good news is, armed with our pseudo inverse, now we can fit it to a lower order polynomial, which is typically the case. Usually when we have 100 data points, we're actually only looking for like a quadratic, right? This is the tool by which we can fit that. So what you do is now, instead of having as many terms as you had data points, you have a lot less. You only have m. In which case now you have m data points with n coefficients. That defines a rectangular matrix And you can just do your pseudo inverse and you can get your answer very nicely. So this is an example that has the true function, which is this here. It's a fourth order. Notice that it's, so this is 3 x to the fourth minus 2x squared. So we're missing the cubic term entirely, plus x minus 9. Okay. What we're going to do is we're going to add random noise to this. And then we're going to try and fit it. So true curve is the blue dashed. Noisy curve is the red. Back in my day, I did an undergrad research fellow, USRA, undergraduate student research associate program through NSERC. And I had a prof, he was in astrophysics, and he actually gave me a very good tip that like 20 years later, I can pass on to you guys. Do you see, so when you look at something like this, where's all the noise? At the bottom, right? Wrong. That's what I thought too. But thanks to Greg Wade at Royal Military College, he pointed out that the reason that you see that is because your curve is kind of going horizontal. There's actually just as much noise with these points. The thing is that it's going vertical. So this point is roughly as far from the vertical drop down as the other ones, but it doesn't look that way because it's going up so steeply. All that to say, when you're visually looking at graphs, and you should always visually look at graphs, right? Be aware of the steep curves because they're misleading. It's visually, you want to see all the noise down here, but it's actually all over the place. By the way,
ask a question?
Yep, shoot.
Sorry. So, the fact that there's like more data points, or is there even more data points at the bottom? Is that also an optical illusion?
Optical illusion.
Okay. All right.
Yeah.
Thank you.
You got it. You could just as easily consider shifting this entire polynomial and rotating it on its side, and then it would look completely different, even though it's the same data. Right? So let's see. Okay. Let's do the Vermond matrix. Vermond matrix is the, Van der Mond. I misspelled that, but Gemini picked it up anyway. For this matrix for a cubic polynomial, if you recall, this is the matrix that looks like 1 x squared, x cubed, right? Cubic, 1x, x squared, x cubed, blah, 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 blah. Let's do it for a cubic polynomial. That's our x. Let's print x so that we can see, although it won't look like this because this is actually evaluated at different x's. What we're going to do is we're going to do our pseudo inverse of x and apply it to y data, which is our y coordinate. And then I'm going to just use the polyfit function, which, as you're going to see, is accomplishing the exact same thing. So if you want to break it down step by step, by all means, otherwise use polyfit in order to do this for you all streamlined. And then we can plot it. Sure enough, for a cubic, this actually looks pretty good, which is kind of funny because we know it's not a cubic. We know it's a fourth order because I showed you what the true function was. This is the Vermond matrix, by the way, and it looks like a bunch of gobbledygook. So I wouldn't even I wouldn't even print that one. Generally, by all means, print the matrix. I can't tell you it's actually going to be useful. Okay. So we get that. It actually looks pretty good. Which raises the question, if we didn't know that this was a fourth order polynomial going into this, how would we know that to fit a cubic? Let's take a look. Let's parameterize this. So we have, I think we have 100 data points. So theoretically, we could go up to a polynomial of 100, right? 99. Let's not do that. Let's just increase the order every time. And let's take a look at these things. That's what this code is doing. I don't think I included any funny functions in here. It's literally just a parameterization. And what it's doing is it's going to print out the terms, all the coefficients, and the norm of the residual. And this is what it looks like. So for the line, So the 0th order polynomial is a constant, right? And the constant is just across. It turns out that the line is actually just a horizontal line because of the way that we're sampling it and because the true function is symmetric about that line. I'm going to go over to who else is my lucky guinea pig here. Matteo. Are you there, Matteo?
Yeah.
All right. Which polynomial do you think is right?
It looks like
Looking
there's
at this data.
it looks like there's a couple overlapping there, but that dark blue one.
The dark blue. And the dark blue is, wait, you mean this one here?
Yeah, like 10 maybe.
Yeah, yeah. So the 10th is overlapping with a bunch of the other ones. So you're right. If you look at the residuals, you can see there's a big drop and then it kind of plateaus. And it kind of plateaus around the 4th order, which is nice. Now we've got a test, except it also plateaued around the 2nd order. So how do you know that this isn't also another artificial plateau? Well, maybe we could look at the coefficients, right? This is coefficients. I think they're backwards here. So this is the highest order coefficients. These are the lowest order. And you can kind of see that eventually the higher order polynomials do level off. But even so, like these guys still aren't 0. I don't actually have a good answer for this. This is me trying to get to you guys that there isn't really a good way. The best way that I've found to do it, there are certain tests. There is something called Ake-Ike information theorem. And it does have like kind of robust criteria for this. I haven't seen like a good accessible way to embrace that. The best technique that I've come across is plotting it and using your big monkey brain, right? Because you can kind of see the cubic isn't really cutting it. You can also see that the residual is constantly decreasing. Anybody know why the residual is constantly decreasing? Why it doesn't plateau, even though we've actually recovered the original equation, and it's actually a pretty good version of the original equation. I'm going to go with Shahad. Shahad, are you there?
Yes.
All right. Any idea why the residual is still decreasing? It's a tricky one. What happens if I got all the way to the 99th order? What do you think would happen with that residual? Let's try it. Exactly. Remember that for 100 data points, you can always fit exactly a polynomial of order n minus 1. So since there are 100 data points, if I did fit that with a 99th order polynomial, my residual would be, Shahad? Any guess?
Going to 0?
Yes, exactly. So consider, again, like as we increase that series, we are eventually going to get to 0. So it does make sense that it's always going to be decreasing towards that direction. What's happening is even though we've struck on the actual polynomial, you can always improve the fit of that noisy data by adding more terms. And that's what you're seeing there. Okay, the next point, and I need to speed up a little bit, is to take a look at the Vermont matrix. So the problem with this polyfit is if you're doing the full order, the exact solution, that matrix is actually notoriously ill-conditioned. Terribly, terribly ill-conditioned. Let's take a look at what it looks like as we increase the order. So this is for, what is this? This is our 10 data points. So we can only go up to a 10 by 10. And let's increase it by polynomial degree. If we're just looking for a line, right? Degree 1 polynomial is just a line. You can see the condition number. Again, condition number is robustly defined because we can use pseudo inverse. Is nice. For every additional degree, it increases by basically an order of magnitude. When we get up to 10, which is the exact solution, it is terribly ill-conditioned. So in infinite precision, we will get the exact solution always 100% of the time, but numerically, it's gonna crap out on us. And this is there was a question yesterday about like, what is a badly conditioned number? This is a terribly badly conditioned number, right? So this is why usually when you look at a polynomial fit, you don't usually want to do polynomial interpolation, but polynomial fitting is okay. Like we saw with the cubic spline, 3 by 3 does actually, you can solve that very well, and you don't get all this frenetic garbage. With the Vermont matrix, you can kind of see that in action. Okay. Radial basis functions revisited. The missing component to the RBFs that I didn't talk about yesterday that's in the implementation is this additional term. The idea is that you have your RBFs are going to be capturing your local behavior of what's going on in your function. But because they're generally tapering off to 0, if you have, I think I've got the example here actually. Do I have it? No. Am I plotting it? No, didn't plot it. Sorry. Okay. If you have a Gaussian, right? This was our example, and it tapers off to 0. That's fine, because all of our kernels are also tapering off to 0. No problem. If you have a Gaussian that's on a slope, right? Probably shouldn't do this in class. Right? If you have a Gaussian that's something like this, you see that there's an overall trend to this behavior, right? Similarly with a quadratic or something else. So what you want to do is you want to subtract. So as a review, I'm canceling Wednesday's class for the Jewish High Holy Day. So look out for the guest. All right, taking this home. What you want to do is you want to subtract off the overall trend. And that way you're removing the global fit from your local features, and you're letting your local features then be captured by all these radial bases. This is the NumPy implementation. Use the NumPy implementation. It's actually SciPy, I think. Right? It's a very good one. The idea is that you have this tuning parameter here. So first of all, you can specify the degree of the polynomial. Depending on your kernel, there are criteria that you have to put in to the polynomial, the certain degree, in order to make it a numerically robust algorithm. They handle all that. You don't need to know that. That's how they can do kernels that aren't tapering off on either side. So some of the kernels that they can use are like lines, not going to show a line, or cubic or anything like that. They can do that because they have that polynomial thing in there too. This lambda for 0, your RBFs are going to go through all your points. For lambda more than 0, it's basically subtracting the importance of those points, those diagonal elements, and smoothing it out. So now your RBFs aren't going to go through all your points, but they're going to be a smoother behavior compared to the other ones. So this is the Gaussian. Actually, yeah. So I added a parabolic to the Gaussian from our toy problem from yesterday. And then I use the RBF interpolator with a polynomial of degree 2. And lo and behold, we get this, which is great, to be entirely honest. So this is our ND interpolation routine. Any questions? One. It's already on. Oh, it's not on there yet? Okay, hold on one second. Right now. So it should be saved to the GitHub now. Oh, that's right, because it's Cuvbe and I didn't update it. Sorry. Okay, so it should be there now. Oh, what was I gonna say? Was that? Okay, try reloading it from GitHub. But it should be there now. Like whenever it sees fit to reload. I was gonna say something else now. I forgot what it was. Oh yeah. Okay. These are all for least square regression for functions. Functions that are linear in your parameters can be fit using least squares. Not to be confused with nonlinear in your unknown variable in X, or I guess that's known in that case, right? You're talking about your parameters. The general case where your function is not known in those parameters. So if you go into the textbook, they're going to be talking about like tricks that you can do for things like exponentials is a great one, right? So you're going to have like your function is a e to the b x. How do you fit a and b? You can do tricks. You take the logarithm. You know how like what you would normally do with this, if you're going to fit it, you would do a log plot and then calculate the line and the intercept and blah, blah, blah. You can do the same thing with linear least squares. You would never do that because there are like normal algorithms in SciPy and NumPy that are just like, just find the solution. Right, and they use an optimization technique. This particular one is something called Levenberg-Marquette. That's basically bisection, but like it's an optimization technique, and frankly, that's the general case. So there are special tricks that you can pull to get it. I don't see the value in learning those because realistically, you're just gonna throw. I forget what the function is, but it's like El Grande find the solution, and it doesn't. It takes longer, because it has to be a more sophisticated optimization routine. And then you have a whole bunch of other problems with optimization. Least squares will get you an answer. It will be the best solution that it can find, which is nice. I've got 1 minute, so I'm going to, all right. So I'm going to touch base again next week and see how this is going. But in the meantime, I'm going to go backwards and go back to the interpolation notebook, because I realized that I was kind of deciding whether or not to put radial basis functions in here or in the next section, which is Cuvbe. But I thought at least in this version, it belonged more in interpolation. So the links are automatically updated, by the way. So the links are just pointers to the files in GitHub. When I'm overwriting the files, then it just brings up the next one. Okay, where we left off, interpolation, as a reminder, you get a curve that goes through all the data points that you give it, and you want the data in between or in the immediate neighborhood of. The problem with the polynomials is how do we get to n dimensions, right? Polynomials you don't want high frequency, you want smaller ones, you're into splines. Now your smoothing kind of kicks up a problem. RBFs are a good way to look at it. I am going to give you the very, very surface layer of this, and tomorrow a bit deeper. RBFs goes very, very deep. They're the entryway to neural networks. We will not talk about neural networks in this class. It's just too much. Stefan's already like, oh yeah. Okay. The idea within radial basis function is exactly the name, radial basis function. They are ND interpolative techniques that don't rely on polynomials. Instead, you apply a kernel, which depends only on the distance, Euclidean distance, so Pythagoras, between whatever variable you know and whatever variable you're examining. And the idea is that if you have 10 of these things spread out in ND space, you can calculate the distance between your unknowns and your knowns and apply some kind of function to it. So the kernels are generally defined like this, and typically you would have one of these bases per data point. 10 data points, right? Your I goes up to 10, and this is the norm, right? We're talking about norms all the time. The norm, which is root squared. Okay. Typically we say, and in this example we're going to look at cases where the kernel is 1 at the data point itself. So you can already imagine what that's going to mean in terms of fitting these things, but you'd be wrong, actually. It won't mean that. In general, that won't be the case. I'll talk about that a little bit later. I'll touch on that. I'm not going to go into that too deeply. Okay. So the radial part comes in because it is the radial distance of these kernels, right? And they are all radially symmetric. Your interpolative function is going to be the weighted sum of your basis functions. Does this sound familiar? When we're doing a polynomial, we are doing a weighted sum of polynomials, of monomials, 1, x squared, x cubed, blah, 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 right? We're going to talk about that a little bit more later because we're going to jump into the cool stuff soon. Okay? To determine the weights, what we're going to do is derive our linear system, right? So we know in general, this is going to be the form of our equation. And we know that y at xi is going to be our known data point yi. Write that out over and over and over again. Here's our vector of weights equal to our vector of knowns. What do we do then? Think about that. I'm going to come to the coding example, and you guys are going to give me an answer. Right? I'm already putting this into practice here. Kernels are typically defined with, okay, so that's the radius, and some kind of tuning parameter epsilon. We're going to come back to epsilon in a second too. These are kind of the common ones. Gaussian is, this is super small. I don't know why it's super small. Oh, there you go. Check that out. Good old touchscreens, right? Gaussian is a Gaussian, hooray. Inverse quadratic is the inverse of a quadratic, and I don't know why this is called multi-quadratic, but it's the square root here. Right? All these are in like Wikipedia, NumPy, SciPy. Take a look there. Determination of epsilon, your shape parameter, is a nuanced question, which means troublesome. A general rule of thumb, though, is to use the average distance between samples, right? So your shape function kind of says how much this point overlaps with this point to determine this point, right? And you can kind of see that it's going to get a little bit messy, but that's kind of a good rule of thumb. All right, let's take a look at the kernels, and sure enough, they're 1 at 0, and you'll notice that they taper off to 0 as they get farther away. This idea is related to a technique called kriging. Kriging is also a similar idea where you assume that your interpolated value is related to your known values by the distance, which kind of makes sense, right? Like if you know something is up here and you're wondering over here, you kind of expect there to be some kind of influence of this point over here because of smoothness, right? So it does kind of make sense. Okay. As I mentioned, in general, like these nice properties, phi at 0 is not always 1. Sometimes it's actually 0. And sometimes phi at r goes to infinity is actually also infinity, right? We're not going to talk about those cases. Take a look at SciPy documentation for those, but it's a whole nother level of depth that actually needs the next lecture anyway. Okay, our toy problem from last time, if you remember, was a sampled Gaussian. Oh, I don't like that already. It's saying no. Oh yeah, no, that's okay. Okay, so this is our true function, very basic Gaussian. We print it and we sample our space and we have the true function. Let's do some RBFs. What we're doing here is, oops, where's Gaussian? Here's Gaussian. This should be down here. Yeah. All right. We're going to use a Gaussian kernel. That should be a D, not no D. All right. I promise no live demos, and here I am. We are defining the Gaussian kernel. That's what this expression is, right? NumPy exponential of negative epsilon r squared. Gaussian, standard Gaussian. Let's say epsilon is 1, right? Because we have to start somewhere. Let's use that one. Actually, there's a good reason why we want epsilon 1, but you won't see that until the next example. This nested for loop is assigning the elements of our phi matrix. So what that means is this matrix here, we're going to build. Yeah. Once we build this, we're looking for this vector. This is our vector of weights, and this is our vector of knowns. How do we solve this? My matrix is a matrix, n by n. N is 11 in this case. We have 11 sample points. We have x, which went into building the matrix, and we have our y vector. Question for the audience. Nobody raises their hand. I'm going to start picking up people. You said something, man. Number one rule. Never say anything. Yeah. You know what? You speak up a lot. You speak up a lot in class. You at the back. Who's not paying attention? Yeah, you. How do we solve this? We have a matrix. Look at me go with my marker. Right? Whiteboard time. I love it. I love whiteboards. If when you guys come to my office, you'll see I have a 4x8 whiteboard sticker on my wall. Love it. All right. We have a matrix, which is psi. We have a vector, which is our weights. And we have our knowns, which are our data points. And we want to solve for this. How do we solve that? Any ideas? We use LU decomposition. We use any of the previous lectures, right? We can always do this because it's just a matrix vector is equal to another vector. Okay. So what I like to do personally is, so this code block won't run right now because it's missing a big part. Okay. And so this is going to be my structure from now on. Let me see if I can zoom in here, right? Here's the question. Here's my hint, and then here's the answer. So let's just scroll up here so that you can't see the answer. First, and it automatically scrolls down. All right, whatever. So I always like to take a look at these things because sometimes you'll actually see quite a lot from here. So just print by matrix, and sure enough, we get this ugly thing. Once we have, okay, so at least we have a matrix. Good. Right? Take it piece by piece. Whenever you're doing these codes, like print out as much as you need, as much debugging as you need, because you'll start to see things. Okay. Now we use LU decomposition, which is weight equals NP dot linalg dot. We can do whatever we want, but the particular NumPy algorithm that we're looking for is solve. Right? And that'll give us the linear solution. And Gemini is already predicting exactly what we want to do. Isn't that convenient? Right? This is honestly, this is why I like the Google Colab thing. Okay. So this is assigning weights being the solution of here, which is what we want. Good. And sure enough, here's what I have down here. So we do that. Did I misspell that? I'm a terrible speller, by the way. But in this case, I just forgot my pluralization. Fitting. We just did RBFs. Hooray! This is our solution. The blue solid line there that's being covered up by the orange is the original function. Red is our data points, and orange dashed is our prediction. And our prediction actually matches very well, which is very nice. This particular case, you'll notice the true function goes to 0. So it kind of makes sense that the kernels, which also go to 0, are going to match that property. The next question is going to be, what if it's a Gaussian with a line underneath it, right? Because then we're going to have a problem at those tail ends, and that's next lecture. We'll talk about that one. I wanted to show you guys a little bit of funny stuff about this matrix, though, because whenever we're talking about LU decomposition, what's the problem with LU decomposition? What's that? It's not sparse, which means it scales as n cubed. So if we're doing RBFs, thank you. If we're doing RBFs of like 11 by 11, no problem. If we're doing it by 1,000,000 by 1,000,000, that's going to be a big problem. This matrix, it's not clear, but if you change the way that NumPy is spitting out these values to have only 2 degrees of precision, you will see this, which is a little bit clearer because at least it's engineering notation, but it's even clearer if you use this keyword suppress is true. That's going to make 0 anything that's below a certain threshold. And when you do that, hey, look at that. You've got a tridiagonal matrix. That's not tridiagonal. What is that, penta? Pentadiagonal matrix, right? Now this is sparse. However, exponential, the Gaussian function never gets to 0. It's asymptotic, never gets there. So this matrix is not actually, this matrix is not actually correct. Technically, with these functions, those are non-zero values far away. The modern implementation of radial basis functions have a neighborhood parameter for exactly this reason. They truncate it when your distance gets too far so that your matrix becomes sparse, and then you can do sparse LU decomposition, or iterative if you want to roll the die. Good. Yes. Bonus marks. What? All right. Let's look at an example of a 2-dimensional Gaussian. So this is completely AI generated. Here's the prompt. Feel free. I think I tweaked it afterwards. So this is going to be an exponential in 2 directions multiplied by a sinusoid in X and a cos in Y. So let's get fancy here, right? Let's do random sampling. None of this equal spacing nonsense, right? And let's throw this in. Let's do the exact same implementation as before. The code is a little bit more sophisticated because we're going into 2D, but rest assured, it generates the same result. This is our original function. You can see it's pretty cool. Red are our sampled points, and here's the result. Does this look like a good result to you? No, terrible. I don't think I actually put in there that it was terrible, but it is terrible. I will assure you guys that my implementation of RBFs is correct. So what could be causing this nonsense? Look at it. This curve, the one on the bottom here, should match this one here. I think it's the alpha. Hold on a second. So alpha is transparency. By the way, when you guys come across these terms, I can at least tell you that. The other thing is that the code is random sampling, so it's actually going to change every time. Just to let you know. Is that clear? So this function does not look at all like this one, right? Okay. What do you think's going wrong? My RBF implementation is correct. What else do you think could be going wrong to cause this type of nonsense? What's it? What's that? The thing on the board. Okay, yeah. So everything kind of relies on this, right? What can go wrong? You've answered enough. I want to hear from this side. The weights could be, yeah. So it is definitely to do with this weighting vector. But what's the problem when you do a solution like that in finite precision? You answer questions too. Somebody who doesn't answer questions. Okay, go for it. I didn't. In this computation, I didn't set it to 0. That was actually only in the printing of the matrix. It didn't actually change the values in the matrix. Is this always going to give us the correct weights? Is this solution always going to be the exact right answer? In a computer? In reality, yes. In a computer, no. Why not? Finite precision, right? How do we know if this solution is going to give us nonsense? Condition number. Bonus points. You guys ever watch the TV show Whose Line Is It Anyway? Yeah, isn't it great? I keep reminded of like the show where the something and the points don't matter. Yeah, the bonus points don't matter. Sorry. Okay, let's look at, hey, look at this. I have a block of code. That's all commented out. Let's look at the condition number before inverting it. And when we run it, the condition number is, what is that? 7.8 million. Condition number is good when it is 1, right? 7.8 million is bad, right? Remember, whenever we do these numerics, we always have that tuning parameter. In this case, that's epsilon, right? Epsilon being 1 just happens. So the rule of thumb with epsilon is that you want it to be roughly equal to the average distance between data points for reasons. It kind of makes sense, right? Like your distance is how much like one data point might overrule the other one, might contribute it, blah, blah, blah. Our first example was equal spacing. Actually, the spacing was 1, right? So epsilon 1 was like the ideal fit for that. Let's calculate. Oh, geez. Touch screen is good for some places and bad for other ones. All right. I asked AI how to generate this and just copied and pasted the code here. Right? Like, by all means, use the tools to generate the blocks of codes, but you have to know what to ask it. In this case, I asked it, find me the distance, the average distance between these data points. And it gave me this code, right? Distance is 0. This is definitely not the efficient way to do this in NumPy because we're using loops. You don't want to use loops. This is quick and dirty and it's easy to read, right? What we're going through is we're going through every single point. We're checking it against the other ones. We're calculating the distance and we're putting it onto a list. And then we're calling what is the average of that list. That will give us the average distance between data points. Let's set epsilon equal to that average distance, which is the rule of thumb. And then we're going to recalculate. And look at that. Matrix condition number drops from 7.8. I am actually surprised that gave us even remotely close to the same answer again. Down to 307, which is much better. It's still not fantastic, but you can see now the function is reasonably well reproduced. It's still actually kind of bad, so let's run that again. That's a random sampling kicking in there, by the way. Give me 1 second here. All right, so at least it's pointing in the right direction. One point of note with RBFs, they have a systemic problem where if two data points are very close to each other, it kind of throws off a lot about the rest of the matrix. And the more like the package implementations of these have countermeasures for that. But that's something that, again, it's like it's too far. What you have to do is like kind of sort all these lists, and then you find like when two things are too close together, you calculate it, you can drop it. There are countermeasures. Just it's too much for us. Yeah. You had a question? Yes. Already had this answer. Yeah. Oh. Yeah. Still kind of bad. No rule of thumb, man. No rule of thumb. Is a fantastic improvement. Whether or not 600 is actually good, it's still not ideal, but it's good. Well, no, it's not so bad. And that's when you have to look into the other countermeasures with the distance between points and stuff to get that down. Okay. Any question with RBFs? This is not how they do it in SciPy, by the way. You have to add one more thing to this, and then you can look at it in SciPy. Any questions? Gonna move on? Okay. Nice thing about RBFs, they scale, they go to ND. There are these sophisticated techniques. We're into curve fit. Goals of this section is to understand how to obtain the best fit for the data for the linear case. I'm going to talk about what linear I'm talking about there because it's not the one that you think. I want you to be able, to calculate and use something called the pseudo inverse. We've actually already mentioned it in class. I should have introduced it then. I didn't, so we're going to introduce it now. And I want you to be aware of the weights. So somebody mentioned weights before. The weights are kind of a hidden layer in this that we need to expose and talk about how to use. In general, least squares regression is basically an optimization routine, right? What we have are some data points, some pairs of data points, xi and yi, and we have some predictor function that we want to fit those data points in the best sense. And I would say that the difference between an interpolation and a curve fit is that the interpolation, you actually expect to hit those points. In a curve fit, you want the best result or the best fit, right? Which kind of implies that there's something stopping you from hitting all of those data points. So there's a bit of implications with what that means. Okay. This notation is going to be a little bit funny the first time, or at least in my experience, I should speak for myself. In my experience, this notation is a bit funny the first time you think about it, but then you kind of, it sinks in and then you realize it. Okay. An interpolation function or a fit function is, so if you have y as a function of x and you have a bunch of parameters in there, right? Your parameters are a1, a2, a3, a4. Your function is actually a function of those parameters and your unknown variable, which is a little bit weird to think about it, but think about a polynomial, right? Parabolic polynomial. You have a function that's a function of coefficient 1, coefficient 2, coefficient 3, and your unknown, x, right? But it is a function of those three coefficients, and those three coefficients are what we're trying to solve for, given all that other data. The general form is we want y as a function of a and xi to be equal to our data points, or we define our residual like we always do, prediction minus the actual answer, right? And we want a least squared fit to that residual. So what that means is that we want to have a solution that is as close as possible to 0, right? In the exact case, the residual will be 0. We're never actually going to get 0 in reality for manifold reasons. Okay, but specifically what we're trying to do is we're trying to minimize, we're trying to find the set of parameters A to minimize the total residual. We're engineers. We don't like working with vectors when we can work with a scalar. So guess what we do? We do the norm, right? Good old norms, right back here again. This is the Euclidean norm. This is literally the distance in the sense of Pythagoras. Okay. In general, it's an optimization problem and it's much more complicated than you would expect. That's why like optimization, we're going to touch on that in this course, but honestly, like people dedicate their entire careers to this. Optimization is all over the place. This is the forum of neural networks, by the way, right? Neural networks, I saw your head perk up there, right? Like any function that makes a prediction that you're tuning to some kind of observation, you want to optimize. Specifically, you want to reduce the squared error, generally speaking. Okay? We're not going to do that right now. We're going to do kind of a special case. We'll see if we get to that tomorrow. We're going to do a special case where y is a linear function of a, not x, a. So I was writing this down, and I have to apologize. I put in this caution note. We're going to pull a switcheroo on the notation here, on the variables. All of a sudden, a is going to be x, and you won't even see the original x anymore. I'll show you what I mean. Okay. Right. In the case where, so consider when we did the polynomial fit, for example, right? Our matrix, our Vermont matrix, was a series of monomials. 1, x, x squared, x cubed, blah, 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 right? And then this was the parameters. A1, A2, A3, blah, 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 right? With the RBFs, our phi matrix, this marker is already dying, was, good thing I have a backup. Yeah, they're probably all dead too. These profs are super lazy. They just like leave dead crap all over the place, right? In this one, look at this, nice bright red, right? We have this, R1, phi 2 of R2, right? Blah, blah, blah. And then again, what we're looking for is weight 1, weight 2, dot, dot, dot. Okay? The X is actually put into the matrix. That's where our coordinate is actually going. A is a function of X. This vector that we normally call X when we're writing like AX is equal to B is not the same X. And I apologize for that. In this case, that X is actually the vector of parameters. And that's just following suit with everywhere else that always defines this as AX is equal to B. And that's the form that we've been using on. But this A is actually an A of our real X. Is that clear to you guys? It's a little bit of a switch. I apologize for the nomenclature. Shoot. Just because everybody else writes down a linear system as AX is equal to B. And I need you guys to make that connection between the linear system and what we're doing here. But it is a problem with the nomenclature, and it's something that I'll have to address in future versions of the course. Shoot. Correct. Correct. This is actually the general form of any kind of function which is defined as the weighted sum of a set of basis functions, right? The polynomials, right? Polynomials are by definition the weighted sum of 1, x squared, x cubed. We use that to form our matrix. RBFs are the sum of phi 1, phi 2, phi 3, blah, blah, blah. We use that to build the matrix. As a pop quiz, anybody know something else that's very familiar to you guys that uses this exact same structure and you could pop exactly into this system? Weighted sum of basis functions. Okay, we're running out of time here. So think about if your data was periodic. Fourier transform, right? In that case, your vector is sum of some weights sine of x plus b cos of x. And you can do the exact same thing. Exactly the same. You would still get a matrix. It's not how it's done. This isn't how fast Fourier transform works. But you could. I got like 3 minutes. All right. I want to introduce the pseudo inverse, and then I'll let you guys go today. Okay. This is kind of neat. When I first read about pseudo inverse, specifically this is more Penrose pseudo inverse, it's really kind of cool. Given a matrix system, AX is equal to B in general, any kind of matrix system, right? A can be M by N, which means you could have, got some examples, right? 3 by 2. So you could have blah, da, da, blah, right? You could have an X vector as long as this dimension lines up. Blah, blah, blah equals blah, blah. Right? This is row by column. What is this? Oh, that's not right. Yeah, no, it's the other way around, isn't it? Yeah. Why do I have that backwards? Yeah. Right? This is a vector this is a matrix equation that you can solve. And I'm going to show you how to do it. Okay? What you want to do is normally you would look for, so you can define your residual, right? You have AX is equal to B, you move B to the other side, now you have the residual is equal to AX minus B. Instead of finding residual is equal to 0, we want to merely minimize it. The way we do it is we say, okay, the residual squared is literally ax minus b squared, right? The norm of it, that's this. We optimize it by saying d by dx is equal to 0. And you can follow the math here, right? Goes down to here. We get this nice expression. We can invert A transpose A is generally a square matrix. If you think about that, a 2 by 3 times transpose switches the order. 3 by 2, you've got a 2 by 2, or vice versa. And as it happens, you can usually invert that matrix for reasons. That's the math part. Feel free to dig into the math. In almost all cases, you can actually invert that. This quantity here is called the Moore-Penrose pseudo-inverse. And it has a very interesting, well, actually you can see from this derivation, right? If you can find the pseudo-inverse, whatever solution you get is necessarily the minimizer, which is really cool. The way that you can calculate it, right? And this pseudo-inverse is actually defined for any rectangular matrix. When we use it, it results in the best fit. And what is the ultimate minimum that you could achieve? You guys talking. Whoever talks in class automatically gets talked to. Gets pulled for question. What is the minimum value of the residual? The pseudo-inverse necessarily includes the real inverse for exactly this reason. So if you ask for the pseudo-inverse and you happen to have a matrix that isn't rectangular, you're going to get the real inverse. They do not calculate it like this. Ethan, you got to perk up this one. Right? They do not calculate, what? They don't actually calculate this in practice. This is actually a matter of, what's your favorite mathematical topic? Singular value decomposition. That's where this thing comes in. That's how they actually calculate this. I'm not going to talk about that one. Feel free to look it up. That's all I got. See you guys tomorrow. Go, go, go. Me too. Shoot. How many projects do you do, man? Go watch TV. Right? Go watch a movie.
So pure Python,
Yeah.
no libraries,
Yeah. Wow, why? Okay. Yeah. Okay. Okay. Yeah. As TensorFlow. Nice. Very nice. Have you tried yeah. I don't honestly I don't know anything about AI or generally fitting neural networks. But well, exactly. Yes. Right. Which is where it comes down to it. But I guess for the nonlinear systems, are you doing stochastic gradient descent? Or how are you minimizing it? Oh, so all of a sudden by no libraries. Okay, okay, okay. But you Googled how to do it. Well, that's fair. That's fair. Well, guess what? We're going to talk about, man. See you tomorrow. Shoot. Yes. Yes. That's fine. That's fine. Yeah. Yeah. That's fine. Yeah, it happens. It happens. Appreciate it. Yeah. Yeah, you too. Don. This is Malik, by the way. This is my high school co-op for this semester. So we're going to work together and we're going to try and figure out how to put these lecture notes onto like a better. Yeah. Like I would love to have like like all this chunky code. I would love to have like locked so that nobody tries to figure out that, but just like, hey guys, just edit this block in the middle and then like run it and actually see what to do. I think there is a way. Pardon me? Possible. Possible. Yes. So that's one option. Apparently, we can also lock certain cells in Jupyter. It doesn't work in Colab. I don't know about GitHub Pages or Binder, but we could actually lock part of them so that you just can't edit it. Yeah. Got a question? Feel free to hang out if you want. I've got to run after this. My kids are waiting for me at home. Sorry, Don. Give me 1 second. Are you going to drop by tomorrow? Yeah. Okay. Cool. See you then. Good to meet you. Yeah. Shoot. I know.